Dear students, today we will discuss about the linearly independent vectors. Last class we discussed a few things about subspaces and some examples, column space, linear span. So all these things we discussed in our last class. So today just we will see what do we mean by linearly independent vectors. A set of vectors, the collection of vectors S, which is equal to v1, v2, etc. vn, is said to be linearly independent if the sum alpha 1 v1 plus alpha 2 v2 plus etc. alpha n vn is equal to 0. Then all the coefficients must be equal to 0. The other way is you cannot express any one of the vector with the help of other vectors. So the system, or in other words, the system has a trivial solution. That means if this is equal to 0, this gives us a system of homogeneous equations. Then the solution of that homogeneous equation is only one, that is 0, x equal to 0. For example, alpha 1 equal to 0, alpha 2 equal to 0, alpha n equal to 0. In other words, if you take the matrix of the columns v1, v2, etc. vn, then if you reduce it to echelon form, or if you can reduce it to the identity matrix, then the system, the collection v1, v2, etc. vn are linearly independent. So otherwise the set is called linearly dependent. Now we'll move to a simple theorem here. So where we have the collection of vectors, they are linearly independent in V. Then every element, if you take any element in the linear span of S, that means if you take a vector which is the linear combination of these vectors, it has unique representation. The proof is, suppose V belongs to L of S, then we know that V is the linear combination of V1, V2, etc. Vn. If V is also in the form beta 1 v1, beta 2 v2, etc. beta n vn, then we have to prove that the weightage of v1, v2, etc. is same. That means alpha 1 is same as beta 1, alpha 2 is same as beta 2, and etc. alpha n is same as beta n. Then only the representation is unique. So according to this, both are V, therefore we equate both the equations alpha 1 v1 to alpha n vn is equal to beta 1 v1 to beta n vn. Now if we shift the right hand side to the left hand side and take v1, v2, etc. vn common, you can write the system as alpha 1 beta 1 into v1 plus alpha 2 beta into v2, etc. alpha n beta n into vn. Since v1, v2, etc. vn, they are linearly independent, alpha 1 minus beta 1 is same as alpha 2 minus beta 2 is same as etc. alpha n minus beta n, that is equal to 0. So this gives us alpha 1 is equal to beta 1, alpha 2 is equal to beta 2, etc. alpha n is equal to beta n. Therefore, that is, the representation is unique. So now we move to the next theorem. The theorem says if v1, v2, etc. vn belongs to V, then if we have the n vectors, then either they are linearly independent or some vi is linear combination of the preceding one. So very important theorem it is. So the proof is, I will take a v1, v2, etc. vn. If I assume that they are linearly independent, then there is nothing to prove. Suppose they are not, that means some of the vector is depends on some other vectors. So then what I will do is, I will select alpha I such that I is the largest integer with the property alpha I not equal to 0. So I am taking the coefficient alpha I for I largest such that alpha I should not be 0. What it means? Alpha I plus 1, alpha I plus 2, etc. alpha in if they are 0. So that is the meaning of this. So I am choosing that alpha I which is not equal to 0. So next I will remove alpha I plus 1, the terms containing alpha I1, I plus 1, I plus 2, etc. in. Then I am remaining with alpha 1 v1 plus alpha 2 v2 plus etc. alpha I vi is equal to 0. Here we know that alpha is not equal to 0. If alpha is not equal to 0, then we can shift the preceding terms to the right hand side, and we can divide those terms by alpha I, because the reason is alpha I is not equal to 0. So therefore Vi can be written as minus alpha I divided by alpha I V1 etc. minus alpha I minus 1 alpha I divided into Vi minus 1. So that means we can express Vi as the linear combination of preceding vectors. Just take a note here. The note is, if the set in R power n, that means the collection V1, V2 etc. Vn in R power n contains a 0 vector, then S is linearly dependent. So it's, the proof is very simple here. So if some of the vectors, say V1 is a 0 vector, then we can write the combination like this. See this, 1 into V1 plus 0 into V2 plus etc. plus 0 into Vn is equal to 0. Then we can see that all the coefficients are not 0. So therefore the set of vectors are linearly dependent, because 1 into V1 is a 0, 0 into V2 is 0, etc. 0 into Vn is also 0. So that means that sum is 0, but all the coefficients are not 0. The coefficient of V1 is 1. So therefore they are not linearly independent, means they are dependent. So next we move to the next concept, that is basis or base of a vector space. So simple definition is there for a basis. A collection S of vectors V1, V2 etc. Vn of V is said to be a basis of V if S is, the first condition is what? It is linearly independent. Those vectors are linearly independent. No vectors depends on other. You cannot express any of the vector with the help of other vectors. So that is the first condition. The second condition is these vectors span the entire space. That means if you take any vector in V, you can express as the linear combination of these vectors. So these vectors span the vector space V. Then we say that the collection is a basis of a vector space V. So the next is a dimension. So dimension of a vector space is very simple. It is the number of elements in the basis set. So the number of elements in the basis set gives us the dimension of that particular vector space. So the problem, we'll take some problem here. So the question should be here, can we write the vector 139 as the linear combination of V1, V2 and V3? Or if possible, you write 139, the vector, as linear combination of V1, V2, V3. So let us check, can we write it or not? So linear combination, I mean V is equal to what? X V1 plus Y V2 plus Z V3. So in place of alpha 1, alpha 2, alpha 3, I took the variables x, y, z, unknowns x, y, z, so that we have a system of equation which we have studied earlier. So the system of equation, if you do that, you will find the system of equation 2x plus y plus 3z is equal to 1, x minus y plus z is equal to 3, 3x plus y plus 5z is equal to 9. So we can solve this system of equation using calculator. You can solve it, or you can write the augmented matrix and reduce it to the echelon form. That way also you can find it, you can solve it. So the solution, if it exists, then we can say that you can write the vector V as linear combination of x1, x2, x3. If the values of x, y, z doesn't exist, then we say that we cannot write y as the linear combination of these three vectors. So if you solve, you can find the solution. Using calculator you can do it. So other way, many methods are there. So augmented matrix you can write it, reduce it to, that is Gauss elimination method. So you can find the solution. So here in this problem we got the solution, x equal to minus half, y equal to minus 5, z is equal to 10. That means we can express V, the given vector, as a linear combination of V1, V2, V3. So we'll move to the next problem, where we have to see whether we can write this vector as a linear combination of these three vectors. So once again, the system is this is the system. Now if you use the calculator and if you find the answers, the calculator may show error. So that means the solution does not exist. Or another procedure is, without using calculator, you can do it. You can use the calculator, but not directly. So the augmented matrix we have to write, then reduce it to the echelon form. When you reduce it to the echelon form, you can find this matrix. So what is that matrix? 1 0 5 4 0 1 16 14 0 0 0 minus 31. Now you can see that the rank of the coefficient matrix means so this matrix is the coefficient matrix. Its rank, if you want to find, you have to find the number of non-zero rows in a reduced echelon form. So this is the echelon form. In this reduced form, you will find 2 non-zero rows. Now if you see the augmented matrix, this is the augmented matrix and this is its echelon form. So the number of non-zero rows, if you want to count, here there are 3. That means the rank of the coefficient matrix is 2, the rank of the augmented matrix is 3. That means the ranks are not same, the system is inconsistent. That means the system has no solution. So the system has no solution means you cannot express the vector as a linear combination of these 3 vectors. So that is the conclusion. So the next problem is determine whether these vectors are linearly independent. So linearly independent means what? X into or alpha, in place of alpha, beta, alpha 1, alpha 2, alpha 3, I took x, y, z. That means x into v1 plus y into v2 plus z into v3 is equal to 0 means we have to prove that x equal to y equal to z equal to 0. That means this system, which is known as homogeneous system, must have only one solution, that is x equal to 0, y equal to 0, z equal to 0, known as trivial solution. If this system has trivial solution, then we can say that these are linearly independent. Other way is, if you reduce the coefficient matrix, it must reduce us to identity matrix. That is, take the matrix A, coefficient matrix. Now if you reduce it to the echelon form, you will reach this matrix, which is 1 2 3 0 1 5, that is with the row elementary row operation. If you perform the elementary row operation, you will reach to this echelon form. You can see the rank is 3, which is number of unknowns. Then you can conclude that the vectors are linearly independent. So these are called pivot positions. These vectors are called pivot positions. So we will find those pivot in those pivot position non-zero numbers means those 3 vectors, first one, second one and third vector, are linearly independent. So other way is you can reduce it to the identity matrix. If you reduce it to the identity matrix, then also we can say that the given vectors are linearly independent. So similarly we have to verify whether these 3 vectors, that is 1 4 9 3 1 4 9 3 12, are linearly independent. So what we can do is we can write the coefficient matrix and perform the elementary row operation, and if you apply the elementary row operation, we reach to this matrix. So you can see that the rank of this matrix is 2, then definitely we cannot reduce it to identity matrix. This means the vectors are linearly not linearly independent. So you can say, since rank of the coefficient matrix is 2, which is less than the number of unknowns, the vectors v1 v2 v3 are dependent, not linearly independent. Otherwise we cannot reduce it to identity matrix. If it is possible to reduce this matrix to identity matrix, then the vectors are linearly independent.